Every method of aerospace propulsion humanity has ever deployed relies on a single principle: Newtonian momentum exchange. To accelerate a vehicle forward, you must eject mass backward. This area chart demonstrates the mathematical ceiling of the Tsiolkovsky rocket equation. As you demand higher delta V, the required reaction mass increases exponentially. Pushing a spacecraft to relativistic speeds requires more mass than exists in the observable universe, a hard asymptotic limit, making it physically unattainable. Our farthest-reaching interstellar probes, like Voyager, remain strictly bound by these static kinematic laws. If the objective is to reach the nearest stars within a human lifespan, the exponential math of the rocket equation forces a choice. We either accept transit times measured in millennia, or we develop a way to navigate space without pushing mass against it. General relativity reframes our understanding of the universe. Gravity is not a central force pulling objects through a static, empty vacuum. Instead, it is a geometric property of a four-dimensional space-time manifold. This grid visualizes the space-time interval equation, where the metric tensor defines the local geometry. A standard mass-energy distribution, like a star, conventionally warps this grid to create the gravitational wells that dictate planetary orbits. Theoretical physics proposes an active approach to this phenomenon, known as metric engineering. If we can artificially design the geometry of the metric tensor, we can induce locomotion without applying kinetic thrust. If the geometry of space-time dictates the motion of mass, then engineering the local coordinate geometry can theoretically circumvent the kinematic speed limits imposed by special relativity. Engineering a metric requires a specific mathematical toolbox. Physicists must break down four-dimensional space-time into a stack of three-dimensional spatial slices that evolve over coordinate time. This equation represents the ADM formalism, describing that slicing process. The lapse function, alpha, determines the interval of proper time. The shift vector, beta sub I, maps the spatial coordinates, defining how the grid slides and shears. By independently manipulating the lapse function and the shift vector, theoretical physicists can construct arbitrary, highly localized geometries in spacetime. The ADM formalism provides the exact framework required to mathematically isolate and engineer a distinct bubble of space. In 1994, theoretical physicist Miguel Alcubierre applied the ADM formalism to design a completely isolated, translating region of spacetime. This is the Alcubierre metric equation, introducing the shaping function f of rs. It operates on strict boundary conditions, 1 inside the bubble, 0 outside. On a 3D surface plot, the space directly in front experiences rapid volumetric contraction, while the trailing edge expands. This creates a topography often described as a Mexican hat geometry. The walls of the bubble exhibit an extreme space-time gradient, bridging the manipulated interior with the unperturbed universe outside. By tuning the shaping function, the Alcubierre metric defines a region of space that continuously displaces itself along a predetermined path. Accelerating an object with mass to relativistic speeds requires infinite kinetic energy and subjects the payload to crushing g-forces. Because the shaping function equals exactly 1 inside the bubble, the interior manifold remains perfectly flat. It is an uncurved patch of Minkowski space. A spacecraft positioned inside this flat region acts as an inertial reference frame. According to the laws of physics, the ship is in freefall, following a straight geodesic path. These light cones illustrate kinematic acceleration versus metric translation. Left, accelerating through space tilts the light cone towards the speed of light. Right, the metric translates, carrying a perfectly vertical light cone. This vertical orientation proves the spacecraft's local proper acceleration is exactly 0. With 0 local velocity, the passengers experience 0 g-forces and 0 relativistic time dilation, regardless of how fast the bubble moves relative to an external observer. The Alcubierre metric achieves apparent faster-than-light travel by moving the coordinate space containing the ship, rather than moving the ship through space. The Alcubierre metric is mathematically consistent, but translating it into physical mechanics introduces severe paradoxes. Look at Einstein's field equations. Standard causality dictates that a physical mass-energy distribution, the stress-energy tensor, determines the resulting space-time curvature. Metric engineering reverses that causal arrow. We dictate the desired geometry first, then use the equations to solve for the required physical mass energy. We input the Alcubierre metric back into the field equations to calculate the specific required energy density, denoted as T00. The calculation yields a highly specific output. Notice the negative sign at the front of the resulting energy density value. A negative T00 value mandates exotic matter, a substance possessing a negative energy density, which pushes space outward rather than pulling it inward. Generating macroscopic negative energy density violates both the weak and null energy conditions of classical general relativity. The mathematical elegance of the warp bubble results in an energy requirement that exceeds the total positive mass energy of the observable universe, demanding mass energy configurations that have no known physical parallel. Quantum mechanics permit minute amounts of negative energy, demonstrated by the Casimir effect between tightly spaced plates. But maintaining the walls of a macroscopic Alcubierre bubble requires exonic matter scaling anywhere from stellar masses to the total mass of the observable universe. Even if you could harvest an entire star's worth of exotic matter, the superluminal boundaries of the bubble exhibit semi-classical instability. Quantum fields at the bubble's leading edge blow up to infinity. The exotic matter cannot keep pace, causing the boundary to violently shear apart. There is also the Krasnikov causality problem. Forming a superluminal bubble from flat space requires forcing exotic matter to move faster than light. To avoid tachyonic motion, you would have to pre-place infrastructure along the entire route using subluminal craft before a faster-than-light trip could occur. A superluminal Alcubierre drive fundamentally clashes with quantum field theory. It is doomed to tear itself apart through infinite Hawking radiation and paradox-inducing causality violations. Recent theoretical work by physicists like Aubrich, Martyr, and Lentz attempts to rescue metric engineering from the exotic matter problem. Their models focus on soliton drives. By calculating a specific shift vector distribution, they theorize that a warp bubble can be constructed using purely positive mass energy. However, these positive energy solutions strictly forbid faster-than-light travel. They cap out at subluminal speeds to ensure they do not violate classical energy conditions. While generating a controlled warp metric remains out of reach, our ability to detect extreme macroscopic metric distortions, like the collision of black holes measured by gravitational wave observatories, is rapidly advancing. Until a unified theory of quantum gravity can resolve these boundary interactions, metric engineering remains a rigorous test of general relativity, mapping the exact mathematical coordinates where our current understanding of spacetime meets its physical limit.